So we're going to watch this brief introduction from Khan Academy about piecewise, and then we're going to talk more about them. And yeah, so hopefully it works.
Like h of y is equal to y squared, or f of x is equal to the square root of x. What we're now going to explore is functions that are defined piece by piece over different intervals. And functions like this are, you'll sometimes view them as a piecewise, or these types of function definitions, they might be called a piecewise function definition. And so let's take a look at this graph right over here. This graph, you can see that the function is constant over this interval for x, and then it jumps up to in this interval for x, and then it jumps back down for this interval for x. So let's think about how we would write this using our function notation. So if we say that this right over here is the x-axis, and if this is the y is equal to f of x axis, then let's see, our function f of x is going to be equal to, let's see, there's three different intervals. Let me give myself some space for the three different intervals. Now, this first interval is from not including -9. I have this open circle here, not a closed-in circle. So not including -9, but x being greater than -9 and all the way up to and including -5. So I could write that as -9 is less than x, less than or equal to -5. That's this interval. And what is the value of the function over this interval? Well, we see the value of the function is -9. It's a constant -9 over that interval. It's a little confusing because the value of the function is actually also the value of the lower bound on this interval right over here. And it's very important to look at this as -9 is less than x, not less than or equal. If it was less than or equal, then the function would have been defined at x equals -9, but it's not. We have an open circle right over there. But now let's look at the next interval. The next interval is from x is greater or -5 is less than x, which is less than or equal to -1. And over that interval, the function is equal to, the function is a constant 6. It jumps up here. Sometimes people call this a step function. It steps up. It looks like stairs to some degree. That's very important here that at x equals -5, for it to be defined only one place. Here it's defined by this part. It's only defined over here. And so that's why it's important that this isn't a -5 is less than or equal to, because then if you put -5 into the function, this thing would be filled in, and then the function would be defined in both places, and that's not cool for a function. It wouldn't be a function anymore. So it's very important that that when you input -5 in here, you know which of these intervals you are in. You can't be in two of these intervals. If you are in two of these intervals, the interval should give you the same value so that the function maps from one input to the same output. Now let's keep going. We have this last interval where we're going from -1. We're going from -1 to 9, from -1 to +9. And x, it starts off with -1 less than x because we have an open circle right over here. That's good because x equals -1 is defined up here, all the way to x is less than or equal to 9. And over that interval, what is the value of our function? Well, you see the value of our function is a constant -7. A constant -7. And we're done. We have just constructed a piece-by-piece definition of this function. And actually, when you see this type of function notation, it becomes a lot clearer why function notation is useful even. And hopefully, well, anyway, hopefully you enjoyed that. I always find these piecewise functions a lot of fun.
What'd you say?
Piece definition.
Because the y value down here is -7.
Why are they all left on?
Because it's in between. They're not all. This is saying x is greater than -1, but less than. You read from the middle one. It's in between. All right. So what he did was a introduction. So that's why they were just constants. Okay, to make you understand that it's over an interval. Does that make sense? Okay, so pieces mean that even though it's all together, it's just that different things are happening along the function at different intervals. So this is an example of a piecewise function. Okay, we're going to go over evaluating piecewise functions. And so the interval tells us which piece of the function we would use to evaluate. Okay, so you look right here, any number that is greater than -3 but less than -2 would go in this section. Does that make sense? Any number, I would use this function to define. Any number that is greater than -2, but less than 1 would be defined on this function. Any number between 1 and 3 would be used on this function. So when we look here, if we're looking for f of -3, so f of -3, which interval would we use? We'll use 1, 2, or 3. We would use 1, right? Because it falls in this interval. So we would use the first equation, which is 2 minus x, but instead of an x, I'm substituting in a -3, which gives me 5. So my answer would be 5. Okay, now we're gonna do f of -2. Which interval does -2 fall on? Why does it fall on 2? That's where it's equal, right? That's where it's equal. It's not equal at 1, it's equal at the second interval. Do we see that? So we're gonna plug in -2, and -2 is gonna go into 1 minus -2 squared. That's gonna give me 1 minus 4, which equals -3. How do we feel about evaluating from a piecewise so far? Okay, all right. If not, let me know. So now we have f of 1. Which interval does f of 1 fall in? It falls on 2 because it says this is where it's equal to 1, right? So I'll use the second interval. So that gives me 1 minus 1 squared, which equals what? 0. Okay, last but not least, f of 2. Where would f of 2 fall? In the third interval. So we're gonna have 2 to the third, which equals 8. Because 2 is between 1 and 3. Okay, so we're looking at where it falls on the intervals, and then that's the portion of the function you use to evaluate. Questions, comments about evaluating piecewise? Doable. Okay, you gotta pay attention to where it's equal to at. Okay, so make sure you're paying attention to where it's equal to at. That's gonna be pretty key for you. Questions, none? All right, now we're gonna talk about graphing. So I'm gonna pass around the little graph sheets that I have for you to grab one because you're gonna need it. So you'll take one. I would probably take either the bottom or the top. The bottom. Just count by what you want, but take a graph, pass it around so we can practice graphing. Which one are you gonna? Yeah, you can on that one.
I think the top one.
The top one. Yeah. Take a little baby graph and we're gonna practice graphing. So it's a sticky. I've had them for a while. I forgot I had them in my room. But they may not be as sticky as they used to be. Maybe get some for your table.
You got 3? No, bro, I got it.
I think my nail's coming off with this one. Like it hurts so bad.
But there's only one. Oh, yeah, you're right. Dang. We need another one.
Everybody.
Oh, okay.
All right. Like, no, we're not separating. All right, so everyone should have a little graph. Now we're gonna graph. So it says here, we're going to graph 0.5x squared from -4 to -2, okay? When you have a beginning and ending, You're gonna substitute these values in to figure out where do they go, okay? We know that our breaking points are the ends of our interval. So we have an imaginary boundary breaking point at -4, -2, 2, and +4. So I like to go in and draw those in. So I'm gonna do my -4, I just do a dashed line. So I'm gonna do a dashed line. At -4, a dashed line at -2, a dashed line at +2, and a dashed line at +4. It's all the endings of your interval. Huh? It's the intervals of your ending. -4, -2, 2, and 4. Okay. After you've done that, you're now going to graph where it tells you. So I'm graphing between -4 and -2, -2 and 2, 2 and 4. Okay. So to get my first value, I'm going to substitute in -4. If I substitute in -4, what do I get? 16, and then what's half of 16? 8. So at -4 on here, I'm going to go up to 8. And it's going to be a closed circle. Why is it closed? Because it says less than or equal to. Now I'm going to substitute in -2. -2 squared is 4. And what's half of 4? 2. So at -2, I'm going to go to 4. 2, is it open or closed? It's going to be a close. So this graph, then I'm going to connect it. And I know that it has a little curve to it because it is a quadratic, which is okay. So there's my first piece done. All right, now I'm going to do the next piece.
8 to 3. Miss, if it goes more than 10, I can't.
Did I not go down to 2?
I'm not with you. No, Miss, you put it at 3.
Ah, fudge sickles.
Oh.
I said 2, and I guess
Miss, but the thing is, you tricked me too. I put 3.
You're supposed to be doing the math, not just relying
I
on me.
was relying on my teeth.
I said not just relying on me. There we go. I thought I went down. Okay. So now we're gonna do the same thing. So this time, we're now on to our second interval. And now we're from -2 to 2. So I'm gonna plug in -2, what I get? -2. So at -2, I'm at -2, and haha, I'm already there, right? So it's just a little doubling up there. And then I'm gonna plug in +2, and that's gonna take me to 2. And it's an open circle. Why? Because it's not equal to, and I'm just going to draw a constant line connecting them. Okay, and now we're on our last interval. So our last interval is going to be, I plug in 2. What is 2 squared minus 4? 0. And so it's going to be a closed circle at 2, 0. Why is it closed? It's equal to. And then I'm going to plug in 4. 4 squared is 16, and 16 minus 4 is 12. So at 4, we're going to go all the way up to 12.
Yeah, Miss, you want to go up to 10. So you make it like an imaginary line?
Yeah. Make it do what it do. All right. And now I'm going to stay within the bounds until I get up there. Pretend that that's the best curve you've ever seen. They're both closed because it's equal to. And it's a little curve because it's a quadratic, and quadratics have a curve. Let me redo that. That's just shameful.
And this graph was funny. And you know what, it looks like an X. Look at, yeah, it's still so short. They're like,
Okay. All right, let me try that again. I'm gonna concentrate really hard.
You can have graduation. Oh, yeah.
Oh, so close. All right. And you now graph your first piecewise function. You literally have to do it in pieces. Okay, hence the name.
peace.
Piece.
Wise.
Yeah, you literally have to do it in pieces. All right, how do we feel about it? A piecewise? Mhm. So we evaluate it and we graph it. It's going to be the same process no matter if your function changes. You're going to identify your interval, your endings and beginnings of your intervals, and then you're going to plug the values in like a piece of cake. Huh? Okay. Questions, comments, concerns? Doable? Okay.
There you go.
We've worked with quadratics, we've worked with linears. It's just now you're merging them together. Okay. All right. Now, piecewise are really useful because they are pretty much real world models. Because in no business are you going to typically have the same value the entire time, right? There's going to be other factors that say, okay, when we talked about earlier, we talked about the immigration, right? There's points in history where immigration was going really quick, right? Where there's like a constant flow of immigrants, and there's points where it was at a standstill. So one single function may not best model that, but pieces of functions may model that. Does that make sense? Okay, so if you look here, it says that this graph represents diminishing returns and overfishing. Okay, so the more fishing boats, the more fish that was harvested, right? But as you can see here, something caused that to change, right? They over harvest, and then what happened? Started to decline on the fish that are being available. So this piecewise describes that relationship. It describes how there was a constant return, how there was somewhat of a give and take, and then, this is where it turned for the worse, diminishing, point of diminishing, and then the diminishing returns, okay? And so it's modeled by this piecewise function. So if we were to look here and evaluate, we're looking at f of 6. Which piece of the function would we be looking at? Will we be looking at the 2x or the quadratic? At the quadratic. So we would use the quadratic to evaluate f of 6. So to evaluate this, so we would have -1/4 times 6 squared plus 4 times 6 minus 4. Okay, 36 divided by 4 is going to give us 9, right? -9 plus 24 minus 4. -9 plus 24 is going to give us 15. 15 minus 4 is going to give us 11. So if there's only 600 boats that are harvesting, then there's going to be about 11,000 fish harvested. Okay. Now, what if you're going the other way? What if it says f of 6? This is saying you're looking at your y now. If you started y, what happens? So if I'm looking here at y, f of 6, which function would I use to evaluate that? I'm following the red. The red is represented by our quadratic. So we use the quadratic to figure out when would I have only 600, will we have harvested 600 6,000 tons of fish. So in order to do that, you would have to, graphically, we can make an estimate. Let's pretend that Ms. Jones can draw straight lines, okay? We're gonna do our very best. So we're here, and we're gonna come down, coming down, coming down, Okay, that did not stay straight. I see it. You don't have to tell me.
We're trying to get hit.
I was trying to keep it perpendicular.
What number?
Fine.
are you trying to-
Wherever it landed, it landed. I feel like y'all are judging me and I don't like it. Hold on.
I'll draw for you.
I'm just gonna use the tool. I'm gonna cheat.
All
All right, yeah. I be trying to do, you know, legit situations over here. And then we're gonna come down.
That's what we were trying to hit.
Okay.
Okay, 7.5.
Shh. Shh.
It was at 9.
I was making a good effort, okay? All right, so roughly, where are we at now? 600s? All right,
Hundreds, yeah, there's hundreds right there.
yeah? Are y'all sure?
It says hundreds right there, fishing boats, hundreds.
Okay,
Am I sure?
well, no, that means I did math wrong. All right, so roughly, I think it's like, is it probably like more 5.5, 5 and some quarter. Who knows? 575, 5 something. But I don't think it's quite 600. I think it's under 600. But that's what you would be doing, is evaluating. And figuring out, based on what you have, where things are falling. What do you think diminishing returns mean, based on the graph? Huh? Okay. So looking at our graph, it says that this is the point of diminishing returns, right? So if this is our point of diminishing returns, what does that tell us? At this point, no longer, it's a change in it's a turning point, right? So for this graph, the diminishing return is a turning point in the function. It's a turning point in the situation. Say, y'all gonna run out of fish soon. And that's what it would be. Okay. So that's how piecewise functions are used on a real world level, for evaluating and making sense of real world data. All right. Questions about that? No?